start today's session. So far, let's summarize what we did through the semester. We've gone through the concept of the inverter. We learned about the topology. We learned about the PWM and how we could control the switches in our topology. Each one of them, either like a half bridge, full bridge, or like even cascading multi-level inverter. We went through the sinusoidal PWM, which is the main kind of like PWM technique that we use because our target is a 60 Hz sinusoidal or desired waveform. We went through the THD analysis and we learned what is the power quality and harmonic distortion means and how we could calculate that and what are the techniques to mitigate that harmonics, either the software technique that we talk about for enhancing or optimizing the switching, and the hardware technique like passive filters that we talked about on our course. We also talked about the different categories of inverters. Either they could be voltage source or current source, and we see in each category what are the differences in topology and the control, and what are the applications, and what are the advantage of each of them when it comes to supplying different type of loads and responding to the dynamic in the system. Now, from now on, we are going to focus on voltage source inverters. Okay, and today we are going to talk about a different type of categorizing the inverters when it comes to actually connecting to a load or to a grid. Okay, so far we are only talking about the inverter itself without supplying anything. Okay, now we wanted to see, okay, what's going to happen if we want to actually connect our inverters into the grid. Okay, for this perspective, we have two categories of inverters. One is grid following inverters, which we are going to discuss today, and the next is grid forming inverters, which we are going to discuss that in future sessions that we have, future classes that we have. The main differences is that it's basically in the name. Grid following, okay, would measure the parameters at its terminal when it connects to the grid or connect to the load. Load is not a good kind of like situation. Basically, connect to the grid and tries to follow the situation, the conditions of the grid. And when I say condition, we have several type of parameters that we measure. We already talked about that, I think, in the first or second session. We have four main values, four main parameters that we have to keep in mind every time that we wanted to like do an analysis or control. One was current, the second was voltage, then frequency, and then power. Okay, these are the four most important variables that we have to like deal with. Okay, voltage, current, and power are basically defined based on the load condition, how much load you have to supply. Okay, but frequency is a natural kind of characteristics of our system. But when I say natural, I don't mean like natural as natural frequency, this concept that exists in physics. I mean inherent. That's a better word. An inherent kind of like characteristic of a system, which we have to keep it solid. Okay, we do not play with frequency. Frequency is the state of our system. Okay, so we wanna keep it constant. We don't play with the frequency at all. Okay, and we don't tolerate very like variations on frequency too. Okay, so that being said, I want to give you another perspective of this category of grid following and grid forming. Since current, voltage, and power are determined by loads condition, okay, what we mean by grid following and grid forming is basically that frequency aspect, these frequency parameters. So grid followings always follow the grid frequency. If the frequency of the grid is 60 hertz, they work at 60 hertz. If there is a deviation, there is a problem in the grid that causes a variation in frequency, grid following inverters also follow that variation and basically get out of the desired state. Okay, grid forming, on the other hand, they don't follow the grid system. They actually indicate, they mandate, they create the desired frequency at their terminal. Now, with that being said, as introduction, let's go through the grid following and grid forming. Okay, this is why is that the definition for the grid following, as we said, is based on the frequency. The grid following inverters are the devices that synchronize itself with the power grid. Okay, and synchronize you mean basically means keep up with the frequency of the power grid. Okay, without a proper synchronization, grid following is basically unstable. It cannot work and it cannot provide uh, a stable, reliable energy supply to the grid or to the load. Okay. Now, that being said, one of the most critical features of grid following inverters is frequency and phase matching. Okay, that creates a very uh, high importance when we talk about the grid following and grid frequency. I added a schematic, like an image, to kind of like give you the intuition, uh, somehow like what I mean by grid following and grid forming. I hope it helps you to like better understand the difference between these two categories. Now, the working principles of grid following inverters, GFIs, okay, are basically uh, very similar because they are inverters, very similar to what we discussed before, with one specific addition. Okay, first of all, they are DC-AC conversion. We already talked about that. They are inverters, so they use pulse width modulation to create the AC and our desired voltage and frequency. Okay, but the addition is, as we said, they have to follow the frequency of the grid, so they have to synchronize itself with the grid, meaning we have to add another component to our control system, which normally we call it phased locked loop, a PLL component. That phased locked loop, which we are going to discuss that, okay, tries to track the frequency of the terminal and synchronize our control system in the inverter with that frequency. Okay. Giving you these information, basically we could say that a GFI is basically a block diagram of a power electronic switching device, which is that half bridge, H bridge cascading multi-level, a box of control loop that controls the voltage, current, and power based on the load condition. We also going to talk about that, introduce the concept of that control today, hopefully if we have time. The PLL block, which basically is essential block for grid following to synchronize, to keep synchronization with the grid. And at the end, as we discussed before, a filter to mitigate the harmonics. So for grid following, we have four, uh, is that four? One, two, three, four. Yeah, four block of components. our main switching device, our control loop, that PWM control loop, which will define and control also the voltage control and power, the PLL block, which controls and synchronize with the grid and controls the frequency inside our PWM. Okay. And so this one, let me see. So this block is basically orders the frequency to this block. Okay, here. Okay. And at the end, the filter to mitigate the harmonic or damp the harmonic because we want less harmonics in our system. Any questions so far? Okay. So far, based on what we talked for those four components, we already discussed the power electronic part, the switching part, and discussed the filter part. So the end block and starting block of this configuration, we already covered that. Okay. Today we are going to talk about these two middle blocks, the control system block. Okay. The phase lock loop. We introduced the phase lock loop and the control system. I have to say, like this today, I'm going to introduce the concept of the phase lock loop and the control loop and basically PID control system. But next week, we are going to delve a little bit deeper into each of those components because they are important factors. They are very important, kind of like parts of our design when we want to like talk about the grid following inverters. Now, when we talk about, let's delve into that control parts, okay? When we talk about the control strategy, okay, the one that include current, voltage, and power, okay, what we want is basically four aspects, okay? It would divide to four aspects. First, active power control, okay? Second is reactive power control. Then specifically current control, and another addition that probably you didn't heard about that before, but it is important for inverters, a fault right through control. Let's talk about that. We said we need voltage, current, and power to be defined based on the load condition. That you already know, and we already discussed that the power are in our list because it's important for us to know how much energy we injecting or we consuming, okay, in a power system. But we all know that the power is byproduct of voltage and current, okay? So when we talk about the AC system and basically three-phase system analysis, okay, what we essentially doing is controlling the voltage and current, and by that we controlling power. But we all know that in power system, because of the AC analysis, we have two type of power. Power here is not a scalar, is a vector. Okay, is a complex number. We know that the power in a power system, in a three-phase power system, is normally is basically is in any alternative system, not three phase. Any alternative system is defined as complex power, which is the vector that is contained the active power and reactive power. Okay, now, so if we want to control power, we want to control active power and reactive power. How we could control that? We are going to talk about the details of the mathematics of that, okay? But if you go over the material that I put over there over the canvas, posted on the canvas, you could find that since power is a byproduct of voltage and current, if you run the analysis over a power system, like run the KVL and power analysis on a power system, you would find that active power, are basically influenced by the phase difference between the voltages from source and load. So the amount of active power, if we have voltage of source and voltage of load, okay, and each of those voltage, let me write down somewhere here. Each voltage has an amplitude and phase. Okay, this is a vector field. The active power normally is influenced, basically is influenced by the phase of these two voltage. So if there is a difference in a phase, that difference in a phase would indicate the amount of power that flows from source to load or from A to B point, and that's it. The reactive power is influenced by the amplitude. Okay, the reactive power is influenced by the amplitude. Uh, the power factor that you mentioned, Christine, in the uh, chat, the power factor is the quality of our complex power, which is defined based on how much active power we have in regard to the amplitude of the whole power, complex power. So this is the uh, power factor. Okay, so it show us the how much active power we have inside our complex power, uh, relative wise. Okay, so that being said, when we wanted to control our terminals, outputs of terminals, we have, as we said, we have four aspects: active power, reactive power, current control, fall right through. By controlling the voltage amplitude and voltage phase, we can control the amount of active power that we inject into the grid and reactive power that we inject in the grid. How? Let's say we have a certain amount of load, okay? So we have a certain amount of load. And based on those loads, uh, we calculate how much active power we have to inject to supply that load. And based on that calculation, using the formula that relate the power, active power, to the phase of the voltages, we defined our phase, our initial phase, radian, not frequency, phase of our PWM signal relative to the voltage that we have in our terminal. And then we could say, okay, if we set these two phase angles properly, we could manage the amount of power that goes through the switching device, goes through the inverters to the terminal. Same goes for the active power by applying the control over the amplitude of the current, the voltage. Okay. Now, what is if we could control the active power and reactive power, which is basically the output of our system using control? So why we need to use current control? That is basically the current control system is basically a protection system. We need to use the current control to prevent overcurrent. So the current control is basically an not output, like the out level, the second level control system that prevent us to drain too much current from our components and basically burn out our system. Okay, there is a question in the chat. What do you mean by phase offset, Christine? Can you explain your question?
When we talk about the power factor, we can change that phase offset by either increasing the capacitance in the system or decreasing inductance, whatever we need to do.
That concept is basically related to the power system management, the power quality in the power system. In inverters, I want to like first. I will answer your question, but I want to first differentiate that aspect with the inverters power control system. Okay, in inverters, we have to follow whatever in grid following inverters, we have to follow whatever we see at the terminal. So power factor is not an important indicator in our control system. We don't care if the system asks us for a poor kind of like power factor situation, high reactive power, low active power. We are providing them. Okay, this amount of power. Now, the
Figured it
power
was.
factor, the power factor that you discuss is actually like a very good point. Through the system is basically the concept of the power factor, the concept of the active power and reactive power. Active power is what actually doing stuff for us. Reactive power is the energy that we spend to create an environment so we could transfer our active power from source to load. Okay, so in a proper system, we have a capacity of S in a specific system. Okay, if we need a higher Q, that means we have lower capacity left to transfer active power. So meaning the power factor is low. So what we do is to use compensations using the capacitor or inductive based on our situation to compensate the amount of reactive power that we want to reduce the Q so we have more capacity to increase the P, which we need. This is kind of like the concept of the power factor in the power system. Did I answer your question?
Um, I mean, ish. I figured it was already different because this is kind of, it seems like the GFIs are at a different I guess step than what we would consider changing the capacitance or inductive in the system or
Yeah.
inductance system. So
Yes, exactly. This is kind of like that power factor, and power factor compensation is a system uh, level kind of like situation, and it's not just for inverters. It is a general kind of like system management. Uh, this is does source impedance need to match load impedance? Okay, yeah. The question is yes, and I want to ask Maddie if you are able to like actually have a discussion about that. I told earlier that the active power is basically a function of the phase, okay, of the voltages in the source, which is basically our inverters, and in a load, which is our terminal, okay, output terminal is, and the Q is a function of the amplitude of the voltage, okay. We don't talk about the Q, we want to talk about the P because we are talking about the matching impedance. Matching impedance, when you said, is basically is a concept of increasing or optimizing how much active power we could inject to our load. Okay, this is the concept of the matching impedance and importance of matching impedance. Now, we said we are using a, a phase angle to control our power injection. So we have our DC source here. This is our, our DC source. We have our switches. Okay. These are our, like, let's say H bridge. And then we have our filter. And then we have our output. This output has a phase angle, which is the terminal phase angle. Okay. And our source, which is here, okay, has also a phase angle when we have the AC signal. Okay. If you draw a reference, let's say we draw the reference here. We consider here a voltage with zero phase angle. Okay. and we have a voltage with theta 1 phase angle. Okay, can you tell me what that means? This theta 1 compared to 0, what is the concept of the theta 1 and the 0 means in this kind of like situation? How we could describe the difference or model that difference in a phase angles using the electrical circuit analysis?
What do you mean? What are you asking for? Like the degree?
No, Maddie asked that does source impedance need to match load impedance in our grid following? I want to have a discussion to kind of like have a better understanding about this matching impedance and what's going on in inverters. Okay, this is our inverter. This is our terminal. We want to inject a certain amount of power to our terminal. This is a theta 2. We decided that if we wanted to like inject that amount of power, a certain amount of power, we need to set our voltage across at the output of our switches at theta 1. Okay, so if the voltage at the end of the switching has a phase of theta 1, when the voltage at the beginning of the switching does not have any phase, so it's 0. What that means, how we can model this difference of the phase angle. I'm gonna give you the answer because I don't want to like bug you so much. The difference between these two theta, it follows the Ohm law. Okay, the theta difference represents the impedance. So basically, if you want to model this block, you could consider a dynamic impedance here, okay, that controls the theta by changing the impedance to change this theta to inject the amount of power, the optimized power per se, okay, at your output. Basically, what you're doing here with the control system, by active control system, you are dynamically matching impedance to answer the power system. Did I answer your question, Maddie, about the matching impedance?
Right.
Yeah, thank you.
Yeah. Yeah. Same goes for the reactive power. In reactive power, yes, this is grid following. We have to follow whatever grids ask us. If grids demands a certain amount of reactive power, we need to adjust this voltage amplitude, okay, regarding this reference, okay, this voltage amplitude, we had to adjust this relative to the voltage of terminal so we could inject or consume the amount of reactive power that the grid needs. Did I also address your second question?
Yes, thank you.
Thank you. Perfect. So these are the concept of the active power and reactive power. So we're working with the voltage, amplitude here, phase here. Okay. To control the active and reactive power, the current control, as we said, is secondary control to as a basically a protection. So do not drain too much current from our switches. They have a capacity, a threshold. Now, let's talk about the fault right through. Fault right through is very important. I planned a full week to discuss that. Okay. But to introduce that, the fault right through is basically a control system, is an additional function in your control system that helps you to control the operation of the inverter when there is a fault at your grid. So far, these three control system, the active, reactive, and current control, okay, they work in a healthy system. They respond to a healthy grid, okay. But what happens if we have a fault in a grid? Then the grid needs to be kind of like the circuit is breaking up, the protection system are working to clear those faults, So there is no stable system. There is a voltage dip. You don't have any a stable system in your grid. Now what to do? Okay. If you wanted to like follow that chaotic fault situation at your terminal, basically it means you have to inject a tons of amount of current. And because it's a chaotic system, your inverters become unstable, which we normally have. What normally happen is the inverters are forced to kind of like seize power, so they're forced to cut themselves out of the system, and uh, if that's happened, basically means gonna be a cascading failure of your inverter power source. Do you have a question, Christine?
I think you kind of already answered it. I was just making sure that in this case, the fault right through protects actually like the substation itself, right?
Yes. Basically, like the first kind of like policy that any source component has when it find out that there is a fault happening in a grid is to break down the connection and get out of that situation. So it would open the circuit and seize the power, okay? So it get out of the grid so it would not be affected by the fault. This is the first reaction of any kind of source, okay? Now, because if we do that, we are gonna lose a huge amount of if in inverters we basically every time it's the fault happen we seize the power and get out of the grid. Okay, if that policy was there to happen, okay, then every time a fault happened we would lose tons of our sources because they are disconnecting from the grid, and that means we are overloading our whole grid. So loads source balance would kind of like become in a critical situation. What we want to do is to keep our source connected to the system while controlling that the fault would not impact our inverters. Okay, so when the fault is clear, we immediately could continue the normal operation. There is some comments. How would motor starts play into? Can you explain your question more, Maddie? I'm not following what you mean by how how would motors? Okay. You mean like when the motor is start, there is a surge of current from the grid, right? And you wanted to see how this is considered as a fault. This is not considered a fault because the surge of the current it is affecting, it is gonna have like a flicker effect on the voltage in the power system, but that surge of the current, the starting current of the motor, is not considered as a fault. Okay, it's basically a rush of a reactive power demands from the motor. So that rush of a current, starting current, is basically a demand of reactive power by motors, okay, to start to create the environment so the motor could get the active power and work. Okay, that is what's happening. When you have a rush of reactive power demand, meaning you have to consume a lot of reactive power, the reactive power consumption would lower the voltage of your grid. Okay, we said reactive power relates to the voltage, the amplitude of the voltage grid. Okay, so if you have a huge reactive consumption, that means your terminal voltage would fall down. Same goes if you have a huge reactive power injection, it would go up. So that rush is basically the grid has to answer that by injecting a lot of reactive power in a huge industrial scale. Motors, they normally have a capacity. Actually, like in mid level motors, they also have that too. Like even in the HVACs at your home, and even in refrigerator also, they have it now. There is a capacitor, okay, as a starter. There's a capacitor by as a starter before for each of those induction motor. Okay, that capacitor provides the rush of reactive power that the motor needs, so it would compensate, okay, that reactive power, so the voltage would not see the effect, the grid would not see the effect. The next question is, the following is going to be a completely different threshold than just a yes. Yes, fault right through is completely different. So it's not a rush of current, is not, there is an actual fault happening there, disturbing the stability of the amplitude of the voltage and the frequency. Okay, there is a very specific definition of the fault. I encourage you to search that in a standards. Uh, when that happen, system gets unstable. Now we have two options: disconnect or control the situation, keep connection so we would not destroy the load source balance. Fault right through control system would give us the ability to act in a second option. Did I answer your questions? Hopefully, yes. Yes, that's true. There is a variety of standard, not just ISO. There's a variety of standard that is because this fault right through and cascading failure is today's problem. Any solution for that is gonna be huge, kind of like innovation. This is today's problem. Fault right through is a very complex kind of like concept. I have a week talking about that. If you don't mind, because if I get to that, I have to explain a lot of things. I'm sorry for that, but I will discuss that. I actually dedicated a week for that for just for fall right through because it's very important. Okay, now let's introduce our topic of synchronization that we said in grid following system. We have a mandation requirement for connecting to the system beside the general control of the current and power and active reactive power control. We have to get synchronized to the grid because our grid following inverter are not capable of uh, creating a frequency and keep it at that level. Okay, so they have to follow the grid for that. They have to rely on grid for that. Okay, now because of that disability of the grid following inverters, we need to synchronize. What we use for the synchronization is the PLL phase lock loop that would read the terminal voltage, find out what is the frequency of terminal voltage is, and adjust the frequency in our reference signal of the PWM. Okay, so we would follow the same frequency. Okay, there are tons of different type of like synchronization. We are gonna talk about the PLL itself, and there are actually like different type of PLL that we are gonna mention. PLL, as we discussed, is a feedback control system, okay, that locks the phase and frequency to the external reference signal. Basically, more frequency than phase, okay, because the phase then would change based on the active power control, okay, but the frequency is important. So this is the definition of the PLL. So it tries to lock this frequency with the grid. What component we use for PLL is kind of like easy to guess. We need a frequency detector or phase detector. This is our first component in our PLL. We need a loop filter because, as we know, all the signals that we read, including the frequency, has some noise and variation. So we need to just kind of like mitigate or eliminate those noise and variations. So when we wanted to like calculate the amount of or measure the amount of frequency at grid, those noise would not deviate us too much. So if we were being accurately on point on estimating the frequency of our terminal and grid. Okay. And when we did that, so we detect the frequency, we filter out the variation, the noises from that estimation. Then we will have a voltage controlled oscillator. Okay. Normally like a BJT oscillator in practice. Okay. That uses the output of the filter, the frequency output of the filter to create a sinusoidal with the same frequency. That sinusoidal would be used to create the reference signal for our PWM. Are we good so far? So this is how PLL works. There are several type of PLL. I encourage you to search on these keywords. SRF PLL, EPLL, Enhanced PLL, Decoupled Double Synchronized Reference Frame PLL, DDS RF. This is the most advanced one, and a Frequency Adaptive PLL, FAPLL. These are different types of implementing that PLL technology, that PLL feedback loop into our system in order to get a better synchronization for our inverters. Search on that. The differences are very kind of like this is the method of the difference. The difference is not in the general method, is on the detail of like how you wanna to like measure the frequency, how you wanna to like mitigate the noises and the variations and this stuff. So there are different techniques on that. I encourage you to like read about that. Yes, Christine?
Um, if we already put a PLL system in one of our power system circuits in what's it called? MATLAB, Multisim, I get it mixed up. MATLAB.
Yeah.
Do you want us to not use that yet?
No. You could use that. Actually, like I already sent you a video in the announcement on MATLAB about the PLL because I wanted you to like, if you want to start before I discuss the PLL, you were able to like do that. So on that video that I sent on the announcement, they actually teach you how to implement a PLL inside your MATLAB simulation. Okay, so use that PLL. You could create your own PLL based on the block that I said, like the frequency detector, the filter, the oscillator, okay? Or there is a already existing block that you can use for your PLL and define like the values, the parameters of the PLL, and use that parameter, use that already existing block on the MATLAB. Uh, we already talked about that. This is the phase lock loop synchronization design. What you have to do for designing the PLL based, okay, PLL based synchronization, you need to have a phase detection mechanism. There is tons of different phase detection mechanism, okay, that extract the frequency and phase in the terminal. Like the very simple one is the zero crossing. The simplest one mechanism is zero crossing. So it would there is a clock that count the time between each zero crossing in power grid, and by that time, by create by measuring that time, they would measure the frequency. This is the very simplest way to kind of like implement the phase detection mechanism. There are a lot of like kind of like most advanced techniques. You could search on that, and I think I already put on the Yazdani voltage source inverters. They discussed thoroughly about the synchronization, different type, PLL itself, and they have like a very detailed description on that book that I posted as a reference for our course. Uh, Loop filter design is not much difference from the concept of the filter design that you already know. It's a LC or LCL loop filter, basically a low pass loop filter that filters the noise. Is the same filter, different kind of like uh, level. Like before, you were able to like you what we discussed was the filter in a power system. Now we are talking about the filter in a, like a control system. So low power system, but same concept. Okay, and the tuning strategy is how to optimize our response time and accuracy for grid integration, which basically means how to adjust our control system. So for this phase detection, okay, how to adjust the values, the parameters in our phase detection. So if the grid faces changes or a dynamic or different states, by adjusting, we could optimize our accuracy of phase detection. The grid conditions that affect GFIs, the performance of GFIs, okay, are basically three main conditions. One is the voltage distortion, because GFIs tends to follow whatever they see in the terminals. Okay, this is the terminals. They measure it and they follow it. So if there is a voltage distortion, okay, it would basically make the GFIs to fall on the wrong track. Okay, so if we have a harmonic, you have a sag or swell, or we have a voltage dips, and any kind of like the voltage distortion could create misinformation and misguide our GFI on how to control and how to inject the power into the system. So this is one of the disadvantage of the GFIs. Next one is the phase variation. If we have any load change, weak grid scenarios that creates a variation or deviation of the phase on the terminal from the values that it should be, then basically is again misinformation to the control system of GFI, and it would react in a different way, in a wrong way, for answering to the needs of the grid. Okay, for all of them, there is a compensation strategy and a mitigation strategy. We are going to talk about that later on in the course in detail, but for now, I just wanted to like give you an impression of okay, what is the limitation of the GFI. Next one is the frequency variation. We said, and we always we're gonna say that we want to keep the frequency at a specific level. We don't tolerate variation from that, but this is our desire. That doesn't mean that the power grid would not face any frequency variation. If the frequency variation happens, you could already, I think, imagine that it would again affect the system here, because that variation in the GFI, because that variation, if it cut up by the PLL, means that our GFI would also deviate from our desired frequency, which is not interested. If the PLL would not cut the frequency variation for any kind of reason, malfunctioning, variation is too low, we kind of like filter out the variation because we saw it's a noise, anything that could happen. If PLL cannot follow and cannot detect the variation, what's happened is that that frequency variation would translate it to the phase angle difference. Okay, is that clear what I mean? Like this is your signal. If there is a variation of the frequency, your signal become a little bit uh, more compact or more wider. That difference, if PLL cannot figure out that there is a difference in frequency, okay, the control system of GFI translate that difference as power demand, as like active power demand, okay, and answers with the injection of the power. Uh, what time is it? I wanted to like make sure. Okay. Now, any questions so far? No? Okay. The challenges that you have to implement the GFI, okay, into the grid is, first of all, the grid instability. If the grid is weak, your GFI is basically screwed, okay? If the grid has faced any type of fault or variation, your GFI is doomed, okay? So this is the biggest problem that the GFI has when it comes to the connection to the grid. Harmonics and basically voltage deviations, okay, or electromagnetic interference that would happen is also one of the weak spot of the GFIs because any distortion would create noise which if we cannot filter out, that means misguiding our GFI, affecting the terminal, affecting the grid, and it's kind of like a negative sequence. It would get worse and worse and worse until the system it will get unstable. That being said, means that in GFI we need to make sure that this is not gonna be creating a harsh situation. We need a more advanced filtering technique and modulation technique. Okay, so we make sure that the harmonics and the noises and interference would not misguide our control system toward to answer to the grid demands. Let me see. There is a question, wouldn't it be? Uh, by implement, do you mean the GFI or Mohammed? What do you mean by implement? Implementing what? Uh, while you are working on that, I want to answer the second question. Is it favorable to weak and unstable grid? GFI is not a good choice for a weak grid or unstable grid. There is a grid forming strategy that we are going to talk about that later on that currently is basically considered as an answer for weak grid scenario. Okay. Uh, Grid forming is more expensive than grid following. So grid following is basically the cheapest version of inverters to implement in the grid. Grid forming is more expensive. They the standard consideration is that the grid forming would answer the problem of the weak and unstable grid, But to be honest, I don't agree with that. And actually, like, it's not just me. There are several kind of like research done that shows that although in some situation grid forming works better, but it would not answer the problem, and we need more kind of like advanced technique or a different perspective of looking from the problem when we talk about the fault right through and weak and unstable grid situation. I hope I answered your question. If not, please let me know, okay? Uh, okay, let's go into that. So far, we talked about the synchronization and the challenges of the grid following, the challenges that grid following would face in the grid integration, okay? Now we said that in our block diagram of the grid following, beside the switches and the filters and the synchronization that we talk about the PLL, okay, we need a control system that controls the active power, reactive power, and uh, current control as a secondary control. Okay, normally the basic control system that you could imagine to use as your strategy to control is a simple PID feedback loop. Okay, the PID controllers, I'm not sure how much are familiar you are with the PID. I am gonna like next week. I plan to like go a little bit deeper on the concept. So don't worry if you didn't learn that. I am gonna cover that as is important. Okay, good question. Let me. I will explain that, Maddie. Thank you. PID, first of all, to answer your question, is stands for proportional integral differential controller. Okay, so what it does, we are going to talk about the detail. What it does is that it would detect the signal, goes to the feedback. Okay, it has three different road to deal with that signal. One is a simple proportion, so it gives it a gain. Another is it take a derivative, okay, and then it gives it a gain. So P, D, sorry, and then is integrate the noises or the signals, give it a gain, and it become the I, and based on the gain, you add these three together, and based on the gain, you could facilitate which part has to have more influence in the output, and finalize a better kind of like more, how to say, more accurate, noise-free feedback to change to control your system. So this is your input, this is minus plus, and this is gonna be your system. Your system is here, GS. Okay, we are gonna talk about the design of the PID, but PID stands for proportional integral differential controllers. Okay. That being said, I am gonna talk about the PID controller, but I wanted to like also, this is a good place to give you the news. I am working with the department to introduce another course because I think is missing. Introduce another course for fall 2025 as a control system. It's gonna be 4413. And I'm going to talk about the control theory, introduction to control theory, and PID, and all those linear control system in that course. So doesn't matter. Now we are going to talk about the PID. PID controller is a sophisticated, actually, feedback. Is this simple, but it's sophisticated feedback mechanism. Okay. And they continuously calculate. What they do is they continuously calculate the error value, okay, as a difference between our desired set point and our measured set point. Okay, and then it processes through the proportional, integral, and differential system. Okay, and that derivatives terms, and apply the correction based on those three terms. I hope it was a clear statement, but I will also, like as I said, I will give you the more details in next week. Why they are important? Because if we wanted to like convert DC power to the AC power, and we wanted to like ensure we have a stable voltage, we want to reduce our harmonics, all those stuff. But more importantly, we want to address the grid demand because we are load to supply. We need to have a control system that continuously in real time measures the output of our system, tracks what we need to meet our desired, which is the terminal of the grid, our desired value, try to process that difference, that error that we have between our desired, our terminal value, and our output of our inverter, okay? And tries to, by a feedback loop, tries to reduce that error and meet our target value. Okay, PID is very simple to implement, but very, very powerful tool. Okay, now there is a lot of role in PID system. Okay, voltage control, current control, frequency control, and maximum power point tracking, MPPT. Okay, this is MPPT stands for maximum power point tracking. Very simple. It doesn't matter what parameter, to be honest. In PID, it doesn't matter what parameter you want to control. You have a desired value, you have a current value, you want to like make them meet at the desired value. So you want to push your current value to your desired value. And you're using a feedback loop to calculate the error and apply the correction. Again, it would have like for example, we have a desired value, okay? We are here, we calculate the error, we find a correction factor, we apply it. Now we have a different value, okay? Hopefully more closer to our desired value. Again, we calculate the error, we find the correction, we calculate, we adjust the output to a new level, the second level, okay? Hopefully we are closer. Again, we calculate the error, we calculate the correction value, we apply it. Sometimes this happens. We overcorrect, we get a little bit far, and then, this feedback goes over and over until we are close enough to our targeted value. Like our fourth step is very close to our targeted value. This is how PID works. This correction value, that proportional integral differential that we talk about, is the process that translate the error to correction value. How you would translate the error to correction value is the PID value, the PID situation. Yes, Christine, you have a question?
Yes, sorry. So this is another device that's like it keeps the system in a loop, kind of like the PLL, or is it actually sequential?
It is sequential, but I wanted to like actually add this to that point that since we in PLL we also talking about a real-time synchronization, because yes, we want the grid to be at 60 hertz or 50 hertz outside of the United States, but there is gonna be a variation. Like sometimes it goes like to 59.9 or 60.1 hertz, there is a variation in frequency. And our system has to follow that variation. Meaning, as I mentioned here, from the frequency control, the PLL loop is basically could be implemented as a PID control. Okay, that measures the value. We have a target. We calculate the error. We try to synchronize ourselves with the system by applying the correction signal. So what we talk about the PLL and how we discuss that in control perspective, you could consider a PLL as a PID control system in a control perspective. So PID doesn't matter what parameters you use. All it does is to calculate the error from current version, current value, and the target value, calculate a correction that you a specific correction, apply that specific correction, see the how much closer we get to the targeted value, and if we need another round of correction, it apply that, and it's a kind of like a sequential real-time scenario that is goes on and on and on and on to address the real-time variation. MPPT tracking is basically in renewable energy system when we want to like try to maximize our power point tracking or our power extraction from our sources. It's very important kind of like part in a solar system. Okay. We are gonna talk about that in system wide. You could search on that, but I wanted to introduce that that MPPT is also could be implemented as a PID. PID is not activated or deactivated, is a continuous kind of like process. So it's a real-time continuous process. So from the time 0 to the time infinity, PID would not take a rest. Okay, it's always try to kind of correct and answer the variations. Okay, let's see. Okay, I put a like a very simple kind of like block diagram. Okay, sorry, I have if by activate you mean making change, yes, it's continuously making change. What happened, this is like the simple diagram of feedback control loop with the PID controller. Okay, this is your real-time measurement. Okay, or basically you're at terminal. Okay, so it's your target. Okay, this is Y is your target. This R is your current situation, current state, whatever value you have at for your parameter. Okay, it try to measure the current states and compare it with the current to target the state and compare it with the current value. This become an error. Okay, when you compare this, it would create an error. So you have a real-time error calculated continuously. Then you go to the PID controller, okay, using a proportional system or integral term or the differential term to calculate the correction value that you want to add to your system, okay, and then it would create a new output at your situation, which is your like second how to say second second value for your current situation. Then again you calculate the difference between the current situation and your reference. Error comes out, PID works, correction comes out, you apply the correction, you have the new current version. Okay, so it is the continuous time equation. Okay, normally what we do is we use the Laplace domain representation to represent the PID controller because it's easier to solve a integral differential equation is going to be a hard equation to solve, we use the Laplace transform to decrease that integral differential equation to a algebraic equation. Okay, and based on these parameters, the Kp, Ki, and Kd, which is our leverages to control the C, the correction signal, we could tune to minimize the variance, overshoot, and settling time, and get to the targeted point as fast as we could. Is that clear? So by tuning, okay, I mean changing Kp, Ki, and Kd continuously in order, or like in a stepwise, uh, in order to make this process of feedback loop more accurate with less overcorrecting by overshooting, that overcorrection kind of like situation that I mentioned in previous slide, with less overshooting and optimum settling time. So fastest possible settling time to get to the desired point. Now, for practical tuning of the PID control, there are several methods. Okay, one is the Ziegler-Nicholas method, which basically is used for the initial value determination for the PID control. Very famous method, very simple to implement. You could search on that. There is an auto-tuning algorithm, which is automatically adjust that the factors, the proportional factors of the, or like the influence weight of the proportional, integral, and differential terms in the PID. There is manual tuning that you change it. Basically, it's like you see the performance and you change the value, check the performance. If it's better, that means you did it right. If not, you go the other way. This is very basic, and actually, like this is the most popular way in industry, and they do in manual tuning. So they don't consider that as like a very silly kind of way. It's simple, but it's very popular. Okay, it worth the cost. But auto tuning is more advanced, and it's basically using another kind of like a more advanced control system in PID, more advanced configuration of the PID. And anti-wind up strategy is also another technique, is relatively more advanced than the three one, the auto tuning, which is try to prevent the saturation from in your feedback theories. Because when you have an integral meaning summing up several components, several numbers. Okay, so when you add and add and add and add several components, there is a risk of saturating your system, and then after the saturation point, it cannot add anymore. It would stay to the saturation point. Okay, so to prevent that to happen, and if that happened, that means you have a very high error of calculation. To prevent that happen, anti-wind up strategy could help to kind of like solve that problem. We are going to talk about the detail of the digital implementation of the PID controller. They are very kind of like advanced components and techniques to implement that. There is a discrete PID equation that you could use that, and this is because the continuous PID equation is on paper. We all know that our measurements are discrete. So for implementation, we need to work on a discrete PID equations, okay, instead of the proportional, integral, and differential. That integral and differential part should be discretized. Okay. Another point that you need to like keep in mind in implementing a digital or like even like a general PID controller is what how you would process the change in your parameters. So your parameters is changing, so going from here to here, okay, and then going from here to here, for example, okay. Now you have two way to follow this change. Either is the precise value, you measure the value of the parameter itself, calculate the change, and then you predict what's going to happen, or like you want to like answer that change, you will answer that change. Another way is the velocity form. So instead of value itself, you work as how fast this value is changing through the time. Okay? And by velocity, you control basically by controlling the velocity, you control the position of that value. Is that make sense? This velocity is more accurate, better system from when it comes to the effect of the noise, because the velocity you already differentiated once your signal, so you eliminated a bunch of noises, and it's basically very ideal for the PWM based inverters. There are tons of microcontroller and FPGA implementation for PID controller. You could actually buy, there are several models. You actually could buy the modules on the market. So it's but if you want to like use a specific type of microcontroller, a PID controller, you have to go over the datasheet in order to see if the PID system, the PID controllers implemented in that microcontroller would not affect your performance and would basically optimize is the optimum version for your situation by doing that Laplace transform analysis. Now, there are several challenges that PID would face. One is high frequency noises, okay, because as we said, PID works based on the measurement of the error from error between the current value and target value. So if you have a noise, that means your error is not accurate. Okay, so you need to answer the challenge of the noise. Basically, they use a filter, or you use the velocity form to address that kind of like high frequency noises. Okay. Another challenge is grid synchronization. We are talking about measuring that both our targeted value and our current value are time varying functions. So they are like either like a voltage or frequency or current. They are continuously changing through the time. Okay. And most importantly, voltage and current, because they have tuned with the frequency of the grid, your measurements also should identify that frequency and get tuned and synchronized with that frequency. Otherwise, the unsynchronization effect would be translated to a higher error value for your PID controller and basically misguide your system toward a different correction with a different correction value. Okay. Same goes for the dynamic load variation. When you have a variation in your parameters for voltage and control, you have to follow that. You have to know that. There are techniques to answer these challenges. We are going to talk about that. Most popular one is the DQ analysis, the DQ form analysis that we are going to again introduce later on to address this the effect of the variations in the PID performance. Okay, I already put some solution for those challenges. We could have a derivative filtering. Derivative filtering is that velocity form that I told you. Instead of uh, uh, value itself, you check the velocity of that value, which is basically means you take a derivative out of that value, okay, from the value itself and the velocity of the change. We have to be synchronized, so PLL also is important for the PID control. And for that adaptive tuning algorithm, as I said, there are several tuning algorithm. One is the most popular one is the DQ algorithm, but there are adaptive tuning algorithm that address that variable situation in load, so you could answer the challenge that PID would face, the PID control would face if you have variation at your output. Now, at the end, because I only mentioned the PID as control system, I wanted to like try this and reserve this slide for kind of comparing the PID that we focused on with different type of control system that we could use also for our purpose. Okay, the PID control, the model predictive control, the fuzzy logic control, and the neural network control are the most popular controls that we could have in our control system. We only discussed the PID, and we are gonna focus on PID because these are like too much, honestly. And normally, in the industrial version, in the actual inverters, no one uses a neural network or like model predictive and fuzzy logic. Why? Because they are computationally intensive. They have the like neural network requires an extensive training data, okay, and like the fuzzy logic is the very difficult to tune, okay. So implementing them are expensive based on the resources and the computational burden of these algorithm. PID is very simple, very useful controller that would give us what we want. Okay, although these three has a better kind of like accuracy than PID, but the difference between the performance of these, the accuracy of these, would not worth the cost that would makes these by these kind of like difficulties that other methods use. Okay, but to be fair, we have to like mention the disadvantage of the PID controller. PID controllers has a limited performance in a complex situation, okay, and nonlinear system. So if you have, because PID controller is basically linear controller. They are inherently linear controller. Okay. You could search on that. I am gonna cover that on the course that I told you that I'm gonna have next semester. But uh, to just know, if you have a nonlinear situation, okay, in your system, PID control would not affect well. That being said, another today's problem in power system and IBR system is the nonlinear complex situation in power system because of the inverters that are integrated in the system. So this is today's problem too. Sorry, I passed my time a lot. I lost the control of the time. Yes, Christine, you have a question?
Yes. So I'm assuming these sensors for the PID control, since you said like at the target, they're going to be in different places in the system.
The measurement for targeted value is the measurement that's happening on a terminal that you connected to the grid for grid following, okay? And the current value of your system is the output of your inverter. So you can imagine the two side of your like the output of inverter is the after switches before filter, and the terminal is when you connect it to the grid, the place that you connect it to grid. So you measure the grid and you want to like follow that. So that's your target. Now you have to change your values in the switching so you would follow that grid target. Did I answer your question?
So so are you saying this is still okay? So like, for instance, um, the monitors for the substations where they have the PLL and the switches and the relays and all that stuff. Is this going to be outside, like the sensor that gives that
No, no.
information to the target? Is
PID,
that going to be
PID,
outside of that?
no, PID is part of your inverter.
No, I know it's
Is
part of it. I'm talking about the sensor that tells you what the target value is.
No, is also inside your system.
Okay, so that's
Yeah,
all in the same like
yeah,
control room where you've got all this set up. Okay.
yeah. Okay, any other question? Okay, if not, again, I'm sorry I lost the timing and I went more than I should. And if there is no question, have a great rest of the day. And I don't know if Taylor, please stay in the meeting so we could like talk. Yeah, thank you.
All right, thank you.